Hi everyone, I'm Phil from My Math Teacher is Terrible. Thanks for joining today. Today we actually have a discussion that's not really about how your math teacher is terrible. Rather, it's a discussion of an interesting problem that I had either with a student or maybe that I found on Reddit. I feel like some of the practice problems I do and some of the questions that I answer in my blog come from both places. Some from the front lines and some from Reddit as well. Okay, so this is a calculus question today. So the problem at hand is this limit problem. Having a look at the problem, we see that we're going to be taking the limit as x goes to 1 of 1 over x minus 1 times the integral from 1 to x of e to the t squared over x plus t dt. There's a lot happening in this problem, for sure. But I feel like as we look at it, we have a chance to exercise what I call calculus thinking. My students who work with me have heard me say that phrase an awful lot. And for me, calculus thinking is sort of like a state of mind where we have a look at a problem and then take a step back before we start doing any calculating to see if the problem makes sense and to figure out where the sticking points are and see if we could actually rephrase those things in terms of stuff we already know, in ways that would make the problem a little simpler and allow us to solve more quickly. Something like a U substitution. There's a calculation reason why we do it, but when we do a U substitution and we actually substitute things in, we see that the problem sort of like cleans up a little bit and actually becomes a little bit clearer in terms of how we might deal with that particular integration problem. There's many other examples, but that's one, and this, I believe, is one also. So with that in mind, let's just take a second to kind of like examine the different parts of this crazy-looking limit. First, of course, is the limit part. Okay, so that means we would actually just make a mental note of what we might do in terms of some of our techniques for dealing with what appears to be a difficult limit. That is, in particular, like the limit laws that we have access to. In this case, we have a product here. So one of the limit laws we could consider is that the limit of a product is the product of the limits. So it could be the limit of this times the limit of this. That might be useful. Not quite sure. We're just taking some inventory about how this might work as we begin to solve. The next part is we have this rational function here. And we see that there's a problem right away. If this integral was not here, I could actually look at this limit problem and put in, the first thing I would do is, we put in 1 in for x and see if we have a problem. And right away we do. We put 1 in here, we get 0 in the denominator, which makes the fraction undefined. And there's no algebra we can do to get around that. And if there's no algebra we can do to get around that, then this limit would be a limit that does not exist because we have 1 over 0. And it turns out if you think about the graph of 1 over x minus 1, we certainly have a blow-up discontinuity at x equals 1. So that's problematic straight away. And then, of course, the third part is the integral itself. We have an improper integral with a variable upper limit. And then we see that the integrand is phrased in terms of this variable upper limit as well as the variable t. So if this were an indefinite integral, that is one with no bounds, thinking about how this integral could go, this would be a two-variable situation where x would be constant with respect to t. But we have a definite integral that pretty much keeps us out of the two-variable situation, as you'll see in a moment. The other thing is that I want to point out that when I do this and look at the different components of a problem, I'm actually also looking for some sort of signal to sort of tip me off about where I might go with the solution of this problem. Since it comes from a textbook, likely, the phrasing of this integral is sort of curious to me. Specifically, if we go back to first principles and we think about something like the fundamental theorem of calculus, Fundamental theorem of calculus is something you usually learn sometime during the integral calculus portion of your early calculus studies. And it has two parts, right? Let's just maybe go over here and just take a side discussion. Fundamental theorem of calculus, FTC, right? One of the parts is that the integral from a to b of little f of x dx is big F of b minus big F of a. This is known as the net change portion of the fundamental theorem of calculus, where little f is some function that's in the integrand, and then big F is the antiderivative of little f. All right, and this is the net change. We also use this when we want to find area under the curve of little f between a and b. We take an antiderivative, put the limits in, and calculate and come up with what the area under the curve is between a and b. Those are the two sort of basic uses of this. And again, the net change theorem is that there's a net change of big F that is this sort of difference of big F calculated at the limits. The second portion of the fundamental theorem of calculus is the one that establishes integration and differentiation as inverse operations. So if we have something like the integral from a to x of f of t dt, notice, not a coincidence. Now, if I take the derivative of this, right, what happens is differentiating this replaces all the t's with x's and drops the whole integration sort of thing, right? So this is actually going to be f of x. Let's make that look like an x. Right? That's really what happens here, is that the t's get replaced with x, and this is really effectively that the derivative is canceling the integration, right? It's canceling the integration. One question that students usually have is like, man, what happens to the a? Well, the a, usually, when we put it into the function, produces a constant, right? So if we actually could integrate this and do it as an improper integral with a variable upper limit, we could do that. But we would have, using the first part of the fundamental theorem of calculus, if I did this integral, if I just called this thing I, right? If the integral part is I would really be, according to this, it would be big F of x minus big F of a, right? Because it's the antiderivative of this, which is big F, and it's evaluated at the upper limit and the lower limit. But if I have an antiderivative and I put in a, which is a number, if I wanted to take the derivative of this thing, the derivative of a constant is 0. So that's really why we don't care what's down here if it's a number. This is really what we care about, it being a variable. So this is kind of a side note. If I calculated this integral, and then I took the derivative of this expression, this is a number because I evaluated this at some number a. But this still contains the variable. So that's really what's happening here. Okay, so let's maybe leave this up here and see if we need it. I'll leave it up there, and then we'll see what happens in terms of running out of room and all that kind of fun video recording sort of stuff. Okay, so this is a side note that I sort of like notice something. Man, the phrasing is exactly the same. Some number, some variable, and you know. Okay, so, but before we go to all of that stuff, let's actually do what everybody does in Calculus 1, which is put 1 in for x and see what we wind up with. So I'm going to say equals with a question mark because I'm not sure this is going to be the solution. Right, I put 1 in here, I get 1 over 1 minus 1 times the integral from 1 to 1 of e to the t squared over 1 plus t dt. Yeah, this is problematic, right? Again, as I did with the rational function, we described this already as problematic, right? Because this is 0. And what about this integral? I really don't want to work on this integral. This is not very easy. But we actually have an escape route here. And the escape route is this. Remember, a property of integrals is that if you integrate from a to a of anything, the integral goes to 0, right? Because if we think about the area, or here, if I put in a to a instead, I put big F of a minus big F of a, that's 0. If I think about it in terms of the area under the curve, there's no width, there's only height. If I have no width, I have no area. That's what this is telling me. So this is pretty interesting. But it's not 0, because I have this. If I have 1 over 0, that's undefined. And anything times something that's undefined is still undefined. This is the problem with being that prevents us from being done with this problem at this point. But it raises a couple of interesting things. Okay. Now, we can actually give some thought to something that we learned in Calculus 2 or Calculus 3 that helps us with limits. In particular, limits involving fractions. And that's going to be Lhopitals Rule. Let's think about that. So maybe I'll put a little box around this guy and see if we want to hang on to this. Now I'm going to make another one for Lhopitals Rule. All right, I'll just call it Lhopitals, right? That says that the limit as x goes to a of f of a over, nope, f of x, pardon me, is f of x over g of x. If this produces an indeterminate form, 0 over 0, infinity to the infinity, tons of things, right? If this produces an indeterminate form, then, if I call this little l, if it produces this, then we can say that little l is equal to the limit as x goes to a of f prime of x over g prime of x. That is, if your original limit expressed as a fraction produces an indeterminate form, this is not the only kind, there's like tons of them. If this produces an indeterminate form, then we could say that L is also equal to the same limit going to the same number of the derivative of the top over the derivative of the bottom. Also super interesting. Do we have a fraction here? And can we possibly use this? The answer is yes. It's not phrased as a fraction yet, but here's where calculus thinking comes in and some sort of like ninja algebra skills, right? So I'll erase this because we know that this fraction is going to give me a 0 denominator and this guy is going to give me 0. And that's problematic. But let's rephrase it and then we'll see what happens. So let's rephrase this limit in the following way. Let's say equals limit as x goes to 1. And when I multiply a fraction times something, this really is going to go on the numerator, right? It's this thing times 1 in the numerator and then the denominator. So let's write it that way and see if this sheds any light on the situation. T, that's the numerator, and then the denominator is x minus 1. Right? This and this are equivalent. We just did some algebra, right? 1 times this goes in the top, this stays on the bottom, all good. Great. Now let's use the information that I erased. When putting 1 in for x, we actually get 0 over 0, don't we? We get 0 over 0. And that doesn't suck because we have this, which is super interesting, right? So this says that this limit is a Lhopitals Rule situation. And, you know, it's cause to celebrate, and here's why. And that's why I left both of these things up here. The top, right? When I talked about this thing, here's what we're going to do with this fraction, right? I'm going to do exactly this. All right, I'm going to do d dx of the top. Oh my God, that's what I'm going to do, totally. And then I'm going to do d dx of the bottom, and d dx of the bottom is trivial, right? The derivative in the bottom is trivial. All right, so let's do it. Okay, so this limit is now, we can now say that it's equal to, and let's take the derivative of this guy. What's the derivative of this guy? It's all the t's replaced with an x. And then I drop the integration because it's the inverse, says the fundamental theorem of calculus. Fine, limit. X goes to 1 of what? All the t's get replaced with x. E to the x squared over x plus x. That's the numerator. All this junk like turned into this. And the bottom. Certainly this one is trivial, right? The derivative of x minus 1 is simply 1. And again, like I said, this is cause for celebration, right? This is a, how did this come out of all of this stuff? Again, we just applied some underlying like first principles. Okay, so now we're well on our way to knocking this one out. We're like, we can see the end in sight for sure. Okay, so anything over 1 is itself, right? 5 over 1, 10 million over 1 is just itself. So I'm actually just going to erase this portion because this is redundant, I would say. And now, let's, well, we can simplify a little bit. Let's do that. This is the limit as x goes to 1 of e to the x squared over x plus x. Oh my gosh, look how cool. All right. And now we're ready to do what we do in early Calc 1. We're just going to substitute in 1 for x, right? So let's have a look. This is, so we dropped the limit. We're just going to put this in here. So e to the 1 squared, right? Over 2 times 1. Easy enough. Right, I have no problems here. 1 squared is 1, so it's e to the 1, which is just e. And then the bottom is 2 times 1, 2. And this is our answer. Absolutely cool. And again, we started out with a terrifying looking situation with an integrand that's difficult if we had to do the integral. But by applying a few sort of base principle theorems, we didn't even have to integrate at all. I didn't integrate at all. I took a derivative because I took advantage of one of the parts of the fundamental theorem of calculus. And that got us out of a terrible jam, right? And before I did that, I just did some very simple algebra to now give me this fraction that enabled me to use Lhopitals Rule. And from there it was smooth sailing, right? We figured out we got this, and that means we can use Lhopitals Rule. I guess I would label this step here the little LH, right? I would call it this. I would call it this. And then from there on, this limit is piece of cake. And I actually had no idea that I would get something like e over 2 as the answer when I looked at this terrible integral. Okay, and that's that. Thanks for watching. Thanks for joining today. I hope you found this problem as interesting as I do. And I hope that you learned something about calculus thinking and about how to not panic when we see something terrifying in calculus. Sometimes we can actually pick it apart and then come up with something very clean and very easy to calculate when all is said and done. Okay, well, I hope to see you guys next time. And thanks for joining. I really appreciate that. Please leave some comments, subscribe to my channel, tell your friends, and I'm going to keep the content coming. All right, take care. Thank you.